live here. And nice. So I'm gonna go up the YouTube live here. And nice. So I'm gonna go up the YouTube live here. Okay. All right, YouTube link is posted. Okay, so let's get started. And so I'll just introduce things here. I should also turn on the recording. One moment here. Record to the cloud. Okay, recording to the cloud. Good. So yeah, welcome everybody to the BerkeleyGW tutorial from the electronic structure workshop. Yeah, just to introduce things to our schedule here. After my brief introduction here, we're going to have Felipe Jornada, a new faculty member at Stanford, is going to be giving us an overview of BerkeleyGW calculations and introduction to some issues, and specifically to the Silicon GW example that we're going to get started with. So then we'll be doing that from 9:30 to 10:30. We'll be in breakout rooms so that you can discuss with one another and also discuss with the instructors. Then at 10:30, we'll come back to our main session, and Diana Cho, who's a new faculty member at Yale, will be telling us about doing beta salpeter calculations with BerkeleyGW, and then we'll have another hour of hands-on activities where we'll do this on, do beta salpeter on silicon again in the breakout room. So we have a team of instructors to work with you here. So apart from Felipe and Diana, there is myself and Brad Barker from UC Merced. And we have, well, yeah, let me allow you to introduce yourself. Brad, you want to say hi?
Hey, everyone. Looking forward to this workshop. It's going to be a lot of fun, I think.
Okay. And then from UC Berkeley and Lawrence Berkeley Lab, we have Zheng Lu. Say hi, Zheng Lu.
Yeah, hi, everyone. So looking forward to the workshop.
Yeah. And we have Meng Wu.
Hello, everyone. I hope I can help you walk through all the examples today.
Okay. And we have Yang Hao Chan.
Hello, everyone.
And in principle, we have also Mauro Del Ben from Lawrence Berkeley Lab, although he does not actually seem to be on right now. Maybe we will see him. Maybe we will see him later. And so, yeah, all of us have been working with on using BerkeleyGW and also on developing BerkeleyGW. Basically, all of us are current or former members of Stephen Louis' research group at UC Berkeley, which is where BerkeleyGW has its start and its home. Okay, so now I'll hand things over to Felipe to get started.
Thank you, David.
Stop share.
Perfect. Can you guys see my screen? Share screen? David, can you see it?
Yep, looks good to me.
Welcome, everyone. We're really excited to have you for this. At least in my case, it's the first time that we're having this virtual BerkeleyGW workshop. My name is Felipe Jornada, and I'm giving first a talk on the general overview of this BerkeleyGW code, and to tell you a little bit of some practical issues related to how to run calculations. And I also like to acknowledge that most of the material that I'm presenting here was actually first put together by David Streba. So this is really a joint presentation to some degree. And I'd like to start with basically a big overview of why we care about BerkeleyGW and why we think that it's a very good code for material science, for physics, and to understand novel phenomena materials. So BerkeleyGW is a code that allows you to compute accurate quasi-particle excitation energies, optical spectrum within the beta-Salpeter equation, and also more advanced techniques involving even nonlinear responses. But it's really a versatile code in that it supports three-dimensional, one-dimensional, two-dimensional, and bulk systems, and even molecular systems. And one of the things that it makes it really applicable to a wide variety of systems is that it supports a truncation of Coulomb interaction and also efficient K-point sampling algorithms. BerkeleyGW, we're also proud that it's an agnostic code in that you can interface that with your favorite starting mean field code. For instance, you can start a calculation with one espresso, abbreviate a Partec, and once your mean field DFT calculation is ready, you can carry out your excited state calculations with BerkeleyGW. It is also a general code in that it supports systems which are semiconducting, metallic, semi-metallic, including graphene, and so on. And we have different algorithms that are suitable for different systems. And the 2 points that I also want to emphasize at the end is that our package is fully free, open source, with the source code readily available for people to access it. And it's also a massively parallel code. We actually put a lot of effort to make sure that this code works on newer clusters, newer high-performance computer centers, and very recently, we actually, the team has also hired a software engineer, which I'm showing here, Mauro Delben, and Mauro has been working constantly to make sure that the code always supports newer algorithm and newer architecture. And to give an idea of things that we can do right now, we can actually run calculations on this one was run 2 years ago on the Core 8 supercomputer on NERSC. And you see here, we managed to scale up to 512,000 CPU cores. So we actually do take into account, and we always push the limit of algorithms to make sure that we can support from the smaller clusters to the very large supercomputing centers in the code. I also want to make sure that we do have a vibrant community. This is actually the number of downloads that we have for version 2.0 and 2.1 of BerkeleyGW since July 2018. And basically our user base is really spread out through all the roles. And there are a number of new features and applications that our code supports. I won't go into the detail, but one direction that people have been exploring recently is, for instance, how we can understand the optical response of two-dimensional systems. So thanks to all of our optimizations that we did so far, we can, for instance, study how the optical and electronic properties of two-dimensional materials, such as, in this case, monolayer phosphorine, may actually depend on the substrate that you put in your calculation. Dana Chiu and Steven Raffaele Emerson recently looking at defects in monolayer transition metal dicohydrogenates, exploring larger supercells and looking at how the absorption spectrum changes and how the defect leads to hybridization in the optical selection rule. People also looking recently in plasma two-dimensional material, and even more recently, Jong-Lu Lee, who's an instructor today, and collaborators looking at how quasi-particle correlation within the GW approximation can actually enhance electron phonon superconductivity within barium, potassium bismuth oxide. So this is just a highlight of some recent science that was supported by BerkeleyGW. Some of them are features that are already public. Some of them are features that will be shortly released as they are tested. But as you can see, we do actually support both larger system, but also pushing the limit to support new physics as well. Before I tell you a little bit of how to run calculations, I do want to really stress a bit of our philosophy for developing the code. So what do we focus on and what do we not focus on? And we actually do focus a lot on code correctness. So for instance, every time that we change the code, we have a system of testing the code automatically to make sure that all physical results do not change every time that someone tries to optimize the code, for instance. So really strive for code correctness. We do support, as I mentioned, to support a diversity of mean field codes from Conrad Espresso, Evident, Paratech, and so on, with a API that other codes can use. We also strive for implementing scalable codes and algorithms, and also as much as possible new physics and features. But something that we do not focus on is having a black box design. So what it means is that we cannot hide the physics from the user, especially because we want to give flexibility in supporting different codes. And because of that, as you're going to see in this tutorial today, we have to understand really what we're computing, how we're computing it, and that gives you a much better idea of how the code is structured and the way that it is. So really today, to understand this, why we're not a black box design and why we have to understand the physics, that basically sets the outline that I'm going to use for today's talk. I will give you a brief introduction of the theory behind. I'll mention basically K-point sampling, why that is an issue. I mentioned screening models for the dielectric matrix, screening dependence, symmetry, degeneracy, how we solve Dyn's equation, and also some particularity related to the real or complex versions of the code. So the first thing is that I want to mention is this brief introduction. And the overall introduction that I want to give you is basically a refresher in the theory. I know that David sent you a PDF of a book chapter, including some suggested reading materials. And basically for this first example of this workshop, we will be computing the GW quasi-particle correction. So we are basically going to be evaluating the self-energy sigma within the GW approximation. And that means that the self-energy sigma is approximated as a product of the Green's function G by the screen Coulomb interaction W. So if we need to compute this, what do we need? Well, we need to compute what is the Green's function G. Yeah, the Green's function G, a spectral representation. That's basically the inverse of the Hamiltonian. So basically the wave functions in the numerator and the energy in the denominator. And this is something that we can compute within DFT, for instance. And the second term that we have is the screen Coulomb interaction W. The screen Coulomb interaction W can be written as a product of the inverse dielectric matrix epsilon by the Coulomb potential V. Within RPA, this dielectric matrix can be written in terms of the polarizability, and this polarizability can be written in terms of Green's function like this. So why am I highlighting this? Well, I'm highlighting all those ingredients. I'm not teaching you because we don't have time for that. But if you basically look at the equation, there's a natural way for how to evaluate things. And the first thing that we have to realize is that the screen Coulomb interaction W, it depends on wave vectors Q. So naturally, we know that all of our calculation will involve sum over the Brillouin zones as involving wave vectors Q. And if you look at this form of the Green's function, you see that it involves sum over wave vectors K and a sum over bands M. So it also means that in principle, if you want to compute this Green's function G, you have to sum over all occupied and over all unoccupied states N. And the other thing that you can naturally see is that if you want to compute the self-energy sigma, the first thing that you have to compute is basically the polarizability matrix epsilon. And in order to compute this polarizability matrix epsilon, we need the Green's function. So there's a natural hierarchy for how these calculations should be done within a DFT code, in a GW code. And that's actually how your calculation is going to work out today. The first thing that you have to do to run a calculation is to perform a mean field calculation using a DFT code. That mean field calculation will output a wave functions, charge density, and also matrix elements of the exchange correlation. Using that wave function, we can compute the dielectric matrix epsilon. And using the dielectric matrix epsilon, we can compute the self-energy sigma. So again, this, the way that equations are written and naturally leads to the way that our examples are laid out. We support, again, a variety of DFT codes, but today we'll be focusing on this particular code called Paratech. The second issue I want to stress is the that of K-point versus Q-point sampling. And if you look at the expression for depolarizability, you see that that involves some matrix element divided by energy difference. And this matrix elements involves basically a conduction band at state K and a valence band at state K plus Q. So how do we typically, how do we differentiate between K and Q here? So typically in the code, we use a convention that whenever you're computing a quantity that is directly obtained from a mean field code, for instance, from a wave function, K, we call that a K point, and that is associated with a regular grid or a K point grid. This K point grid, for instance, all the wave vectors K at which the conduction bands are evaluated, that can be, again, an arbitrary grid. It doesn't have to be gamma centered. In the example here, this grid is all the set of blue points that you see. However, the code also needs another grid, a grid of all transfer momenta Q. And again, we define the Q as the grid that naturally appears when creating all possible differences between K and K prime. So for instance, you look at this particular K and this particular K prime, this other K, that gives you one wave vector and so on. And also you can see that naturally K, if I set K prime to K, I'd always have the point of Q going of Q equals to 0, which means that the grid of Q points is always a gamma centered grid. And in general, it looks like this figure over here. So there is again, there's a way that we differentiate what is a K point grid and Q point grid. One is maybe shifted in general, and the other is has to be gamma centered, and it involves different of two K points. In practice, and especially for today's tutorial, we are actually going to use the same grid for both K points and Q points. So basically, without by losing a little bit of generality today, we're going to make this grid of K points to be gamma centered and to look exactly like this one that we have for Q points. There is one problem still that we have to be mindful of. And one is that the problem is that if you look at the dielectric matrix, especially as Q goes to 0, it has this kind of form that you're seeing over here. So if I take, for instance, a particular matrix element associated with the plane wave index G equals to 0, the dielectric matrix looks like 1 minus Coulomb interaction times the polarizability matrix. And of course, you can see that you cannot evaluate this at Q exactly 0. In fact, for vanishing Q for semiconductors, this goes as 1 over 0, and this term goes as 0. So you have a 0 over 0 sort of indeterminacy. What do we do to solve this problem? So what we do is that we cannot include exactly the point Q equals to 0 to compute the dielectric matrix. So what we do is that we use a trick. We evaluate the dielectric matrix at a very small wave vector, but this very small wave vector is still finite. For instance, we use Q of the order of 0.001 in crystal coordinates. And then what we do is that we can basically separate what are wave functions associated with conduction states and wave functions which are associated with valence states. For instance, this plot over here shows which are the grids which are associated with conduction states. Those are the blue dots. And the grid here in green shows which are states which are associated with valence states. And you can see that the difference between points associated with valence states and points associated with conduction states, or vice versa, they're different is this wave vector Q. And this wave vector Q, again, may be arbitrarily small. The way that we tell the code which sort of grids to use for these two calculations is actually to specify two different input files. So the code actually has one input file called wave function. That is the one that we use for all the conduction states. And we have another state file called WFNQ, which includes all the K points associated with valence states. So another way to look at this is that if you want to compute the polarizability matrix that looks like this, we're basically computing transitions from valence to conduction states at 0 temperature. So if you have a finite wave vector Q, you can directly evaluate these transitions involving conduction to valence band, and you can basically take conduction bands and a valence band from the same regular grid from this WFN file. However, if you want to investigate and compute the dielectric function for a very small q, you basically tell that it's not q exactly 0, but rather that it's a very small q. And the way that you evaluate this quantity is that you use your same regular grid for the conduction states, and for the valence states, you use a slightly shifted grid, and that is stored in a file WFNQ, so that it can accurately compute those sort of transitions and evaluate this polarizability for arbitrarily small wave vectors. The way that that works in an actual calculation is that in the input file of called epsilon.n, which is the file that tells the code to compute the dielectric matrix, what you're going to see is that you have to specify all the q points, basically all the set of wave vectors q. And the first wave vector is the wave vector associated with q equals to 0, or q going to 0. So you see that this first line is slightly different than the other ones, and it has a flag 1 at the end. And this 1 at the end tells the code that this is the dielectric matrix to be computed at a very small but finite wave vector q0, and all the other flags are 0, which means that this is the dielectric matrix to be evaluated for the regular non-zero wave vector q. In this workshop, we'll be dealing with semiconductor, for which this particular trick works, but I want to emphasize that if you have a metal with a finite density of state at the Fermi energy, then this trick doesn't work, and you cannot use this sort of shifted grid. So I then urge you to look at the manual or the full workshop that we had in 2019 to see how to deal with metals instead of semiconductors. So the question is now, now that we know that we basically need two different files, one called WFN and the other is WFNQ, how do we actually generate those, all the set of wave vectors Q? So the good news is that you don't have to do that manually. We have a code called kgrid.x. Basically, kgrid.x tells you, with kgrid.x, you specify what is a regular grid that you wish to use, what is a shift Q0 that you wish to employ, and the code can then automatically output for you what is the set of points that will be used for this wave function file, WFN, and what is the set of k points that should be used for this shifted file, WFNQ. And this code also knows how to use symmetry to basically fold the k points into a irreducible wedge of the Brillouin zone. So this is basically what those figures are shown here on the right panel, but I won't talk about that in details. We also have a somewhat comprehensive table. I won't go over this in details, but the question is, how many bands do you need for each particular calculation for which wave function file? So I'm going to leave this as a reference, but I think that you're going to understand that better by actually doing the calculation of the workshop by yourself today. So the next topic I wanted to address is screening models for the dielectric matrix epsilon of Q. And the issue is the following. If you look at the dielectric matrix epsilon GG prime, it roughly looks like the following. It roughly looks like the Coulomb interaction 1 over Q squared. And then basically the sum over valence and conduction k points, which has some sort of energy denominator and those matrix elements in the top. And of course, the Coulomb, screen Coulomb interaction matrix W is simply the inverse of this dielectric matrix epsilon times the Coulomb interaction V. So we have one problem now still when evaluating W, even though the evaluation of epsilon we managed to solve. And the problem is that this W actually diverges for semiconductors. So if you look at something like silicon, we know that epsilon for silicon is 12. So epsilon inverse for Q going to 0 is well behaved. It's 1 over 12 roughly. But this Coulomb interaction diverges as 1 over Q squared for a semiconductor. So this matrix W of QQ prime, it has a very complicated behavior. It diverges for semiconductors. But on the other hand, it's actually finite for metals. So it has a very different analytical behavior depending on the system that you have, even though at the end of the day, integrals involving W, of course, they have to be finite at the end of the day because your self-energy should be finite. To complicate things a little bit more, not only does W diverge, but But W diverges in different ways depending on the different matrix elements G or G prime that you're looking into. And I mean, just to show how things can be complicated, if you have a semiconductor, the G equals G prime equals 0 diverges as 1 over Q squared, but the wing, which is defined as G equals to 0 and G prime non-zero, diverges now as in a vector form, as vector Q divided by Q squared, and so on. And this also gets more complicated as you deal with semi-metals and whether we have two-dimensional, one-dimensional, and so on. So of course, trying to brute force do an integral of a quantity that diverges is a futile exercise. So what the code does is try to help you with that. And in order for the code to help you, you actually have to give a hint to the code. And the hint to the code is you have to tell the code whether you're dealing with a semiconductor or with a metal, or say with something that looks like graphene. So in short, what happens is that depending on which system that you have and which hint you give to the code, using those different flags, the code assumes that W of Q will either diverge as 1 over Q squared, or will diverge as 1 over Q, or be a constant, and employ then different techniques to try to integrate out the Coulomb interaction times the matrix element over the Brillouin zone. I want to emphasize that this sort of hint and this model that we use to solve this integral, it's still fully ab initio. We're basically trying to help the code to make sure that your calculation converges faster with respect to k-point sampling, but your results should not depend on the details of your models if you actually converge your calculation. But anyways, always make sure that you pick up you use the accurate model, screening model for the code, for the kind of class of system that you have that is consistent with the density of state, and always check that the result is converged at the end of the day. The absorption code, as Diana Chu will mention afterwards today, follows a similar strategy also to deal with the divergence of the screen-Coulomb interaction. And I also want to mention that if you have anisotropic materials, you should in general pick a direction for Q so that this direction of Q better captures the average behavior of the dielectric matrix for that particular modulus of your wave vector Q. So for instance, you may want to pick between two high symmetry lines, for instance, this wave vector Q. One topic that I just want to briefly mention is that the code also supports different schemes for truncating Coulomb interaction. So for instance, if you have a molecule, a zero-dimensional system, because we're doing calculation with periodic boundary conditions, the code is actually implicitly doing a calculation where you have a molecule in a box and those boxes are repeating themselves. But we actually have a scheme that allows you to truncate the Coulomb interaction if you have a zero-dimensional system. So basically, we cut off this sort of long-range interaction, spurious interaction between repeated unit cells with this cell box truncation. The same thing if you have a one-dimensional system, such as a nanotube, you also have a flag that called cell wire truncation, which truncates this spurious interaction. And also if you have a two-dimensional material, such as graphene, which looks like this, and it's periodic along this X and Y direction, but is confined along this Z direction over here. You have this option called cell slab truncation, which truncates the Coulomb interaction and all spurious interaction along this confined Z direction. A few other topics I want to mention. The first is how we deal with the frequency dependence of the dielectric matrix. This would just a brief discussion. If you actually look at the full expression for the self-energy as a function of, for instance, frequency, you see that the self-energy involves a sum over orbitals, but an integral over frequencies. And so you actually have to evaluate the screen-Coulomb interaction and convolve that screen-Coulomb interaction with basically your Green's function. So what that means is that in principle, you have to evaluate the dielectric matrix, this guy here, over a very fine grid of frequencies, and that can be actually, in general, hard to converge. So the code actually does allow you to do this explicit calculation, this explicit integral, and that is known as a full frequency approach. But the code also allows you to simplify things for you and to use what is known as a plasmon pole model. And a plasmon pole model says that this dielectric matrix epsilon inverse of omega, instead of you having to evaluate that for all frequency points, and that'll be basically a complicated function, The option that the code has is that it can fit that to a model. And this model basically says that it has, for instance, single pole. And hence, you actually only need to do one calculation. You only need to do a calculation of the static polarizability of epsilon equals to 0, and provide the code with the charge density to basically fit this model for the electric function epsilon inverse as a function of omega. So this model, which is the plasma pole basically approximation, we will be using that in the workshop today because it's basically slightly faster and easier to converge. But please take a look at a more recent at the manual and more recent calculations to see how you can actually do this calculation also without this approximation using this full frequency approach. Some other topics I want to mention briefly. One is asymmetry and degeneracy, which may be surprising for many users because that's not an issue that appears with DFT calculations. And the issue is that when we evaluated the Green's function of omega, for instance, we know that that involves the sum over all bands, and something looks like this, some sort of basically a Brahim cats over all the unoccupied and occupied states, and then we have basically a Green's function, which looks like 1 over omega minus the eigenvalue. So essentially, in all of our calculations, we have to sum over all bands to properly evaluate and construct the Green's function. But the question is, what happens if you have two bands which are degenerate, which have exactly the same energy? If you have two bands which have exactly the same energy, then there's an ambiguity of which bands would be included in your degenerate space. So just as you have a px and a py orbital, which are degenerate, if you include only px and not a py, your results may change if you run on different machines, because another machine may not find that the two orbitals are px and py. They may think that it's p plus or p minus, for instance, in terms of the harmonic, spherical harmonics. So to protect you, the code actually enforces and it makes sure that whenever you're computing physical observables, they only include a set of bands that form a non-degenerate subspace, or rather that you're not slicing a degenerate space in half. The code also has a utility for you called degeneracy check, and the degeneracy check utility tells you how many bands you can include in your calculation so that you're not violating this degeneracy issue. For instance, if you run this utility and the phi wave function, it tells you some general information about that, but it tells you how many bands you're allowed to use in the calculation for epsilon sigma. So for instance, you can use 4, 8, 14, up to 32 bands. So for instance, in this example, even though you may have more bands in your calculation, you are technically only allowed to use 32 bands without slicing any degeneracy space. You can also use a flag called degeneracy check override to turn off this enforcement. And this turning off this enforcement is typically okay if you include many unoccupied bands, because the error that you're making this breaking the degeneracy vanishes as you're basically making an error at a higher and higher energy band, which contribute less and less to your quasi-particle self-energy at the end of the day. So we only have two more issues that I want to mention. One is how to solve the Dyson equation and computing the self-energy sigma. At the end of the day, what we want to evaluate is the quasi-particle self-energy EQP. And in order to compute the quasi-particle energy, we start with a mean field energy computer, for instance, from Consham DFT. And we have to include a correction. And this correction is basically putting back in the right many-body self-energy sigma computer within the GW approximation, and subtract out basically the self-energy computed at the mean field level. The issue, however, is that the self-energy operator sigma, it's a non-local and is also an energy-dependent operator. So in principle, you should solve this self-energy operator and evaluate that for the same energy as that you're solving for at the end of the day. So how do you solve that if you don't know the right result? So there are two approaches, and the code outputs them for you automatically. One is called EQP0. EQP0 is sometimes called the on-shell approximation. It means that it evaluates the self-energy at the mean field energy instead of the quasi-particle energy. That's the definition of this EQP0. EQP1 is another solution which uses a linearized approximation for the self-energy. So basically, it linearizes this sort of self-energy operator and solves for this linearized solution. And this solution for this linearized problem is shown here in this box. So basically, those two solutions are split for you in this sigma hp.log and also in this file EQP0 and EQP.1. In general, we trust much more EQP1 for reporting band structures. Sometimes looking at EQP0 may be good, for instance, for lifetimes in other quantities, but basically for quasi-particle energies, quasi-particle excitation energies, EQP1 is the most trustworthy number that you should be looking into. The other issue that I didn't mention is how do we subtract the mean field self-energy? Well, it turns out that the right self-energy that we have to include is basically the GW and the Hartree potential, and the Hartree self-energy. And the mean field approximation, say with DFT, also has the Hartree potential, but it also has another one, which is the VXC. So basically, the subtraction of the full self-energy with the mean field approximation is the GW self-energy minus the exchange correlation potential that is used by your DFT code. So basically, the code BerkeleyGW needs to read in what are this operator, all those matrix elements, VXC. BerkeleyGW allows you to specify two forms of VXC. One is as an operator in a binary format, and we call this file this capital VXC. And that basically computes or contains the operator of the exchange correlation functional in G space. And that's because if your functional is low quantity space, you can basically Fourier transform and you get a single vector. And if you do that, BerkeleyGW will automatically compute matrix elements associated with this exchange correlation operator for you. The second option is that it can also compute and pass to the code another file called vxc.dat. This is an ASCII file instead of a binary file, and it directly computes the exchange correlation operator, but the matrix elements associated with this operator, which are these ones. So if your DFT code can compute those matrix elements for you, you can also provide them for you. One question is, how do we deal with hybrid functional? If you're interested in doing calculation with hybrid functional, please talk to one of the developers, because the question is how you can make sure that these exchange correlation functionals actually include the non-local part of your functional due to the hybrid. So there are ways to do that, but it's not as straightforward. And the last issue that I want to talk today is involving real and complex version of the code. And you're going to see that when you compile BerkeleyGW, you're going to see there are a bunch of binary files. Some of them are, for instance, called epsilon.real.x, and the other is known as epsilon.complex.x. So why do we have those two basically versions? Well, we call those two versions two different flavors. Basically, the code can be run in the complex flavor or real flavor. The complex flavor is general, it can work for any system. But the real flavor is faster, it uses less memory and also less disk space. When can you use the real space version? Well, you can only use the real space version if you have both inversion symmetry and time reversal symmetry. You should usually have time reversal symmetry in your calculations, and inversion symmetry, it has to be such that the inversion symmetry is not associated with a fractional translation, namely that the inversion symmetry is about the origin. So if you run a calculation with Partec or Quantum Espresso, the code will tell you whether you have inversion symmetry. And if you try to use the complex version on a system that has inversion symmetry, the code will tell you that you could be running a faster calculation. If you're using the real flavor, but you don't have inversion symmetry, the code will tell you that you're doing something that is probably not okay, and your result may be wrong. So always pay attention to what the code tells you and what is the output for different wrappers. So those are the main points and technical issues that I want to raise today related to how we can run a calculation, which are all those technical details. I want to stop right now in my presentation. We have some extra slides related to how you can run, if you wish, calculation on metals, half-shifted grid, and so on. But now I actually want to go ahead and show you how to run the actual calculation in silicon. Actually, as just one extra slide, if David doesn't mind me spending an extra half a minute or so, I do want to mention that if you're interested in also GW calculation, if you have experience on such systems, my group, which just started on January 1st, is actually has open positions for PhD students and postdocs. So if you're interested, we're looking forward to pushing the limits of what can be computed and accessing new physics. So send me please an email if you're interested. So I'm now switching gears, and I'm not going to quickly tell you how to run the calculation on silicon. And I want to acknowledge that this example was first put forward by also David Strube, but this has been a change quite a lot in the next few years, and I really want to thank all the other amazing structures that are working here today, including Brad Barker, John Lee, Ming Wu, Ian Hao, and Diane and others who I may have forgotten. So in the example that we have today, we're going to run your first calculation with BerkeleyGW, and you're going to be plotting and computing the quasi-particle band structure of silicon. And if you want to think about the kind of elements and how the data flows in the example today, this diagram shows pretty much what's happening. Basically, you're going to do a calculation with with a DFT code, and that's shown here in blue. And this DFT calculation is going to be run today with a code called Paratech. And we're choosing this simply because it's slightly faster for this example. So the way that we do this is that we first have to run a self-consistent calculation that basically gives you what is the ground state charge density. And once you basically found the ground state charge density, you never run a self-consistent calculation again. You fix that for all your GW calculations, and you basically generate your file WFN, WFNQ, which includes a number of different bands. You also compute the charge density, the exchange correlation matrix elements, and at the end of the day, we're also going to generate a file called WFN5 for the band structure calculation. We're going to run epsilon code, which require those input files, sigma, and ETQP at the end of the day to plot an interpolated quasi-particle band structure. You should be able, at the end of this tutorial, to compute two things. One is the wave vector dependent dielectric function for silicon. You are going to be able to basically compute the dielectric function of silicon and the inverse dielectric function, or inverse of the inverse, that is known as the macroscopic dielectric function for silicon. You should be able to compare that to experiment and try to argue why that is too large or too small compared to experiment, and whether the dispersion that you have is physical. And you'll also be able to compute a band structure for silicon. You should be able to show that silicon is an indirect band gap material with a gap of roughly 1.137 computed within the approximation that we're using today. And this is shown here in the right panel. So what are the goals for the workshop? The basic goals is to understand basically the relationship between K-grid, Q-grid, and how the wave function flows between different codes, epsilon, sigma, and TQP. And then you should be able to run this GW calculation for silicon and compute a band structure at the end of the day. If you have time, there are some stretch goals. One of them is to recompute this calculation with Hartree-Fock or static COSAC, compare the results and see if they are physically meaningful. Modify the example also for another system such as gallium arsenide, and if you wish also, you have time to redo the calculation with other half-shifted grids. I think that you didn't have any instruction so far how to log into Cori, but the way that we suggest to run the workshop is by using Jupyter, which is a web interface that gives you access to both the files and both the terminals. And Jupyter is actually very convenient because it allows you to easily see the band structure plots at the end of the day. So what you want to do is go to the jupyter.nurse.gov, log in, click on this button to start a Jupyter node. After you start, scroll to the bottom, click at the button to open a terminal. Oops. After you open the terminal, basically type the following commands. This command goes to the Scratch folder. All your calculations should be run in this Scratch folder. You're going to run this command to copy the workshop example, the silicon example, onto the Scratch directory. And then you're going to change directory to this workshop example in your local folder to run everything. You can also navigate through a workshop folder using the nice interface that you have. So first click on your favorites. There's going to be a Scratch folder, and then click on this Silicon GW example. Once you do that, you're going to be able to see all the files associated with the workshop example. And this example is mostly self-paced. So there are a number of README files. If you click on those README files, you are going to see the instructions that you have in each of those files. And so in the same terminal, we can have, in the same interface, you can have the terminal to run the calculations, that README file to see what are the instructions. So please follow these instructions and good luck, and we'll be happy here to assist you. And I hope you have a great time doing this workshop, and that you can run this paradigmatic band structure of silicon and be able to reproduce those results. Thank you all, and we'll be now happy to assist you if you have any questions for the next few hours.
Okay, thank you very much for that, Felipe. So let's say, if anybody has any very general questions, or especially about how to proceed, ask them now. Please know, as I put in the chat, so we have these slides are up now on the workshop website, so you can look at these to refer to anything that was talked about. I also put the path on Cori to where you find the tutorial files in there. And so you'll find there one Silicon GW. That's what we're getting started with. Does anybody have any general questions about how we're going to proceed right now? Okay, so in that case, I'm going to turn off the recording. We're going to